Good morning, everyone. Thanks very much for coming to today's presentation. Today, we are very pleased to have Dr. Chitchanok, Tiansup here to give us a presentation on speculative execution and cache attacks. Chitchanok has made a lot of efforts in terms of publications and research grants. She has received a lot of grants from institutes like ARC and Google. She has published many papers on top security conferences and other conferences like machine learning and others. So I think that now I'm going to handle the session to her. Let's give her a round of welcome applause. Thank you.
Well, thank you very much for the invitation, and I'm very happy to be here at Monash University. And yeah, since we have quite like a small group of people here, so if you have any questions during my presentation, please feel free to raise your hand, because I prefer that you understand, not just like me finishing my presentation. And I hope that for the first part should be accessible to you. I hope it is fun. So if you have any questions, if you don't understand, please feel free to ask. Okay, so yep, the title of the presentation is about speculative execution and cache attacks. But before we go into the details, I would like to mention about my research interest. So I'm interested in efficient and secure crypto system. And my research spans over these three main directions. So for the first one is about efficient implementation, like how to make our crypto software runs faster or use less memory. And the second direction is about cryptanalysis. So with the crypto system, how can we be sure that our crypto system is secure, like mathematical security and so on. And for the last direction is about security. Well, crypto system, it's about sensitive information. So we want to think about security as well. And it could be in a broader way, not necessarily about crypto system. It could be about computers, about the machines. How can we be sure that, well, the machine itself behave like what we think it should behave? And I have some work span all of these directions. And of course, this is not an exhaustive list because I stopped putting it at some point. It's a bit messy. So yeah, but for today, for this presentation, I will focus on two of my work. So one from cryptanalysis and one from security. So the first one, the title is The Gates of Time, Improving Cache Attacks with Transient Execution. If there are many key terms that you don't understand, don't be worried. So I will try to explain what these are. And the second one from more cryptanalysis is about evict spec time, exploiting out of order execution to improve cache timing attacks. So you can see here that there's a repeated word on cache attacks. So, yep. So now this is like my research in general and what we focus on today. To get into more detail, well, before that, I need to acknowledge my co-author first. So these two authors, we have the co-author from other universities, from Tel Aviv, Adelaide, Georgia Tech, and from Ruhr University, Bochum, and me from Melbourne. Okay, let's get into more detail, but let's start with motivation. So we are from computer science, so let's take a look at computer revolution. So many, many years ago, even before I was born, I have to say that. So there's this Apple IIe, and the processor speed at that moment is like 1 megahertz, and memory latency is 500 nanosecond back then. And now, many, many years later, I didn't update my size previously, so it's still 2020, so I'm sorry for that. But we can see that the processor speed has improved a lot, way, way a lot. Like 3,700 megahertz and times 20 because we have multiple cores. But on the memory latency, well, it decreases like from 500 to 50, but the gap is quite large in the sense that the improvement in terms of processor speed and the decrease in terms of memory latency. So there's huge gap between this. So how can we bridge this gap? There's optimization techniques, and one of the ways is that we use locality. And when we say locality, we have two types. The first one is spatial and the second one is temporal. So for the first one, we say that we're talking about memory. So when like previous one, when we mentioned about processor speed and memory, if we need to transfer the memory between the two, how can we bridge the gap? So we say we divide the memory into lines. So this is, you can think of it as a unit into line. And then we store the recently used line in a component called a cache. If you go back to like your computer architecture lecture back then. So yeah, we have cache. So let's try to visualize what's going on inside our machine. So we have memory here, and we divide the memory into lines. And then we store recently used lines in a cache, which is closer to processor compared to the distance between memory to processor and cache to processor. And when we want to use the data, we check if the data is in the cache. If it is there, we say it is a cache hit, and we can serve the data from the cache to the processor. But if it is not there, then we call it is a miss, and then we need to get the data from the memory, which is farther away. It will take long time to get the data from the memory. We bring it to the cache, and then after that, we can serve the data from the cache to the processor. And another improvement, so there's a concept of share cache with, for example, with multi-core processor, that we have the same cache, but then we share between cores. Now, in general, so cache is more complicated than that. So I visualize here as like a one-dimensional, but it's a bit more complicated. With modern processors, we try to optimize even more, and we have the concept of set associative caches. So how it works is that, so now memory lines, they are mapped to a particular cache set. So here, if you look at the figure, so now I have two-dimensional, so I divide it into way and set, like cache way and cache set. And memory line, they are mapped to a cache set. And each line, they can only be mapped to a particular set, but it can store in any of the ways. So there's a mechanism to decide which set to go to. And then with that particular set, it can store in any of the ways that is empty. And because cache is much smaller than the main memory, so there's the cases where many memory lines that are mapped to the same cache set. So let's see what's going on. So in this example, we only have two ways, but we have three lines that are mapped to the same set. So when the first one arrives, like the blue ones arrive, everything is empty. So it just take one of the way, no problem. When the red one arrives, then another way is still empty. That's fine, no problem. But when the green ones arrive, it's already full. So one of the data that is already there must be moved from the cache. So we call it, that part is evicted. And you can kind of recall that one of the paper is called evict spec time. So this kind of mechanism that this evict something from the cache. Okay, so we have, I hope that you have rough understand about how caches work. So now let's take a look at something that I hope it to be fun. Well, before that, I will introduce this right now because this is part of the background, so that you know that, but then after I will introduce my work. So with the concept of cache, like things being in a cache and things removed from the cache, then we can use this as a way to attack. So I would introduce this attack called prime and probe, and this is from back in 2005, but I hope you can get the rough understanding of attack before we move to attack that I present. So for this prime and probe to work, so we have on the right-hand side, we have a visualization of the picture of the cache and memories that we have seen before. And the first step for prime and probe is the preparation. So an attacker, or we call spy in this case, they access all lines in the buffer. So we have memories here. So we attack, or an attacker access all the lines. So the idea of the first step is to set the cache to the known state, because initially attacker, they might not know what's going on. So they want to kind of like reset or reinitialize to the thing that they know. So they access the buffer to fill the cache. So now they know that the cache is filled with their own data or the data that they know. And the second step, they wait for the victim to execute, to do some work, which might access the memory. So what's going on is that during the victim execution, victim might use some data that is not in the cache, because the cache is already full. So if it uses data in the cache, nothing happened. But if it happens that they use the data that is not in the cache, then it needs to get the data from the main memory. But because, again, the cache is already full, then some of the data must be evicted. Now, the last step is for an attacker to check the differences between the setup state or the preparation or the prompt state and the probe state. If everything is the same, then an attacker knows that the victim only accesses the data that is already in the cache. But if it's not the same, then the attacker knows that the victim must access the data that is not in the cache. And how can an attacker knows whether the situation between prime and probe is the same? They know because they can access the original data that they use at the prime step, and they measure the time. Again, if it is already in the cache, then they can get the data quickly. But if it is not in the cache, if it has been evicted, then an attacker needs to get the data again from the memory and bring it to the cache. So there's timing differences between here. So this is the main idea of cache attacks, to cache timing attack, to be more precise, like to check the timing, the time differences, and an attacker can know whether the data is in the cache or not in the cache. And if by knowing whether it's in the cache or not in the cache, or which cache set, if it happens to relate it to the secret, that is how we can get secret information or sensitive information. Okay, so now I really finished the background, and let's move to something fun. Different story. So now I want to introduce a logical state. So we have caches, and now I want to associate what I call logical state of a cache. What it means is that this logical state to say whether a particular we associate with the address and whether they are in the cache or not in the cache. So if that piece of data is in the cache, or that address is in the cache, we set the logical value to true. And if they're not in the cache, we set a logical value to false. It's just a logical state. I'm not talking about the real data. It's just state whether they are in the cache or not in the cache, and set it to true or false. And with that, we can play a bit with whether the data is in the cache or not in the cache. And inside the machine, so they have special instruction to somehow remove the data from the cache, or flushing instruction. So which means that if we use flush instruction, then we set state to false, because flush will remove things from the cache. On the other hand, if we access particular memory, then it will need to bring to the cache. So it will set state to true. But again, if the cache is already full, then that particular memory will be true, but some other piece of memory that is already there could be evicted. So we might evict some other memory. So, and if we want to measure a time, like access time, it means that we need to access that piece of memory. And by doing so, then we bring it to the cache as well. So by measuring time, we also set the state to true. So this is kind of a setup. Are there any questions about this logical state? Just attaching a state, whether the data is in the cache or not in the cache. Yes.
How do you measure time? So if you need another second thread or second application, can you start? I wonder how this works when you have. Yeah, I don't know.
In general, so I mean, there's a like an instruction. So I mentioned flashing instruction, but we could have a function to get the time at this particular moment. So we.
That takes an awful lot of time.
Yeah, but I mean, so, but then the overhead will be roughly the same. So if we call start and stop, so of course it will not be zero. If we subtract, it will not be zero. But then start here and stop here, it will have somewhat roughly like overhead, or even if it's not the same, the differences between cache hit and cache miss is so large that the small tiny will not affect that much. Well, it depends, but I mean, well, I mean, you could try to do it, but I mean, so if you access it once, automatically it will bring to the cache, because if you do it again, then it doesn't help. If it's missed in the first place, then it will always hit after the first one. Are there any other questions? If not, well, let's really do something fun. So I have this piece of code here, and it's only 3 lines, so I hope you can follow. And I want to know what is the cache state of out here after the execution. So there are 2 cases at least. Whether what's the value of in, right? Because it's conditional access, so depends on what's the value of in is. The first case is easy, so I give you the answer directly. If in is not 99, so the condition if in is 99, then it will return, right? So if in is not 99, meaning that it will go to this line, then out will be accessed, meaning that out will be in the cache. So the logical state will be set to true. You see this? All good? Now, what if in is 99? What's the logical state of out? False? Or if the first case is in, then you would assume that the second case is false, right? But because I'm asking, so you don't want to answer, right? So it turns out that it's not that straightforward, and it's actually depends. So there's another keyword in my title about speculative execution. So now we need to understand what's going on with speculative execution. It's another kind of optimization. So we try to speed up performance of machines. So we do a lot of optimization, not we, but someone else, like architecture people. So they said that before we know the condition of the branch, so we have this condition, if it's a branch, like return or continue. So it takes time to know whether the condition is true or false. And if you remember back then in computer architecture that you need to fetch memory, decode, execute, and blah, 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 and there's a pipeline. And if you have branch, then you store all the pipeline. So they don't want to stop or store the pipeline. So they try to predict ahead what's gonna happen. So yes, if you try to predict future execution, and if the prediction is win, then that's fine. Just continue with what's happening. But if the prediction is false, like if there's a branch here, you predict to go here, but it has to go there, then it needs to roll back so that it can change to a different path. However, even though they change the path, but the microarchitectural state stay the same. What does it mean, microarchitectural states? For example, cache. So cache is something hidden in the sense that programmers, they don't need to know that cache exists. They can program without knowing, but it is there just to improve the performance. So the state or what is already in the cache, it will not be removed even if the condition is false. The fact that it has been fetched from the memory stay the same, but it just don't use that data. It doesn't use the data. So that's why I say that microarchitectural states stay the same. So now, if you know about spectral attack, so you might be familiar with this line of code, but if you are not, so I will explain here. So this is quite common when you want to access an array, that you want to check that it is in the bound. So you check whether the index is less than array length. If it is less than, then you can access array at location index. But it turns out that with the discovery of speculative attack and with speculative execution, they try to predict ahead of time whether the condition is true or false. So it could be that inside if they're executed, even if the condition is false. So when the condition is false, they just never use the data. But the fact that it's already accessed, well, it's already accessed, but they just don't use the data. So that's what happened with speculative execution. So if we want to go back to our example, so we need to think about conditional speculative execution. So we have speculative execution and we have evaluating branch. So speculation terminates when we know the outcome of the branch. So there's no need to speculate anymore because we know exactly which branch needs to be taken. So now let's bring back our questions here. What if in is 99? What's going on here? So there are two cases. The first one, if in is in the cache. So if in is in the cache, it means that to check whether in equals 99 or not, this can be done quickly because they get the data from the cache and then compare. So, and well, if in is 99 and branch can be resolved quickly, then this piece of code does return, meaning that out will not be accessed. So it should be false. But if in is not in the cache, to do this comparison, they need to get in from the main memory, bring to the cache, and then do the comparison. The condition will be resolved slowly, meaning that before the condition is resolved, with speculative execution, they already access out. So it's kind of like, okay, if in is 99, the logical state of out could be either true or false. It's kind of weird, right? Well, with the same data, but then the outcome could be different. So with this concept, if we do a simple truth table, if in is in the cache, then out, so the first case, if in is in the cache, out will not be accessed, so out will be false. But if in is not in the cache, so if in is false, then out will be accessed. And are you familiar with this table? Yes? It will, ideally it will be like that. So I mean, if we set up the state, if there's no like other like a program like try to intervene with this one, it will be, well, it's it's like that, but because this is kind of the concept of weird. I don't want to say the word because I will give out the answer for this one. So it's kind of like it's a weird situation that the outcome could be like this, but because of this weirdness, we can exploit it a little bit. No, yeah, it's always, yeah, it's not a percent, it's always. But I mean, so the concept is like this, so that the table is always like this, but then if you can see here, there's a rest condition between how quickly the branch can be resolved and how quickly or how far the speculation goes, or how fast speculation. So this is something that need to be adjusted, because it's not, well, if you try on this machine and you try a different machine, so this table, well, ideally, conceptually, the table is right, but you might need to adjust something to make it like this. Yes. Instruction that it has earlier, like can't it be like true and true? Because like it also like check, right? So if you have an instruction before this condition, so yeah, so yeah, that's correct. But so I forgot to mention that I just set state to false at the beginning. It could be like it could be that the state of out is true initially, and even if it is not accessed, it will stay true because of previous condition. But if we say everything at the beginning is false, then there's an access and there must be like something bringing in. So that's like initial setup. I still haven't got the answer, but I will just give you the answer that this is a NOT gate. So what I want to say is there's a concept of weird gate that you can use this weirdness to construct gates. And this is an example of how to construct a NOT gate. So then why should we stop at a NOT gate? We can try something more. For example, we could try to rearrange or rewrite code like this. So we have two if conditions and before we access out. I will give you some time to think about it, and then I will show the truth table. And if you disagree, you can tell me. But I'm pretty sure I checked it already. So, but you can still tell me anyway in case I make some mistake. And from this truth table, anyone would like to tell me what kind of gate this thing is? Sorry? Not or? Yes, it's a NOT gate. So what if we look at this? So if either of in, like in 1 or in 2 is true, then the output will be false. Because if either of these are in the cache, then it will resolve quickly, then it will not reach out. But only if both of them are not in the cache, it will resolve slowly. So that's where out will be accessed. Another one. So we just have, we need to access in 1 and in 2, and then either return or access out. Here is the truth table. Any guess? No? Yes, it's an AND gate. So yeah, so only if both of them, because we need to access both of them, if both of them are in the cache, if both of them are true, then it will resolve quickly, so out will not be accessed. So once we have not, we have NAND, or if we have NOR, then you can imagine that we can build any gates from this. So we can use cache, we can play with cache, and we can build any arbitrary circuit with this. But before we go to that, I want to mention this multiple output. So it is very sensitive in the sense that, as I mentioned in one of the earlier slides, that when we access something, we already bring it to the cache. So if we have output and we want to know, we need to access. So we already destroy the original was the value there. So some cases, we need to have multiple outputs. And we can build that by accessing. So instead of only one out, so we access two out. So to set the value at two places, we can have multiple outputs. And here is illustration that we can have multiple outputs for this one. Or we can, once we have this, then we can really make something big or something fun. So we try with something rather small, but not that small. We try with 4-bit LU, like adding 4 bits. For this case, we use more than 1,000 gates, and the accuracy is okay. It's quite accurate, 80 to 90%. So after having fun with 4-bit LU, we try to do something bigger. We try SHA-1. And this is only one round SHA-1. It is already more than 2,000 gates. And the accuracy is quite good. So, but it's only one round SHA-1. And for those who know, we even try something bigger. We try Game of Life. And this one, more than 7,000 gates. But this is only one generation for Game of Life. Accuracy is somewhat okay. And here is an illustration of Game of Life. The Game of Life is like after some time you check whether the current cell is live or dead, and you like change the surrounding cells. And yeah, that's and keep repeating, like going on, and live and dead cells will like changing value. So yeah, so this part is what I say. Hopefully it's fun and accessible, but then in terms of research, why do we care? Why do we, yes? Yeah, sure. We are not there yet, but yeah, we are an attacker.
I was going to say that you are not the owner of the device is running some program.
Yep. So exactly. We are not there yet. So this is kind of like a preliminary of my research. Preliminary of this paper, let's say that. So this part is what I say is hopefully it's accessible. Hopefully it is fun, because it's not much of attacking yet. It's just like setting the state. There's like nothing more, but we will get there to the attack. Any other question? So you want to see an attack? No problem. So yeah, so before the attack, so in general, with cache timing attacks, the ones that I gave an example, prime and probe. So if you remember, there are 3 steps. So the first one is prime, just to set up the cache to a known state so that we can compare later on. Second one is to wait for a victim to do something. And the last one is to probe and to check whether it's the same as the original state. The thing is, at the probe step, we need to measure time, right? Because we need to know whether it's in the cache or not in the cache. So we need to have time measurement. And one of the countermeasures for these cache timing attacks is to reduce the resolution of the clock. If you imagine a race, like a sprint running, short distance running, I don't know the number, but maybe 100 meters, maybe, and you measure the time, and you use like a wall clock with like that, tick, 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 and everyone will enter the finish line with 9 seconds. If you don't have 9.12, 9.35, 9.78, you will not be able to determine the winner, because everyone will enter at 9 seconds. And that is the countermeasure. You reduce the resolution so that you cannot, you cannot distinguish between cache hit and cache miss, because it will, if it show like 9 seconds, then you don't know whether it's 9.1 or 9.9. 9.1 could be hit and 9.9 could be miss, for example. So that's a problem with cache timing, well, countermeasure, and we need to overcome this. So with this technique, gates, we can amplify in a sense that we can make create more distinction between like a, well, even if the clock resolution is so low, but we can amplify and get to see the differences between hit and miss. So that is what help with attacking. And we can do this amplification using a NOT gate. So with a large fan out in the system, we have NOT gate. So instead of having one output, we have many outputs. And we can do it like that, for example, for 8 outputs. And when we want to read, we need to read all of them, not just one. So we amplify. So if we have one NOT with 8 fan out, we amplify the signal by 8, because we need to read all 8 before getting the final one. And we can even make it layers. So if we have 2 layers, then we amplify by 64. And if we have 3 layers, by more than 500, and so on. 4 layers, 4,000. So with amplification, we can make a distinction between cache hit and miss even like larger. So here is an attack that you're waiting for. We call prime store attack or high resolution prime and probe. It's similar to prime and probe, but we amplify the signal and we decouple some parts, which I will explain more. As in prime and probe, so the idea is we have the setup phase to know what's the status, like initial status of the cache, and then we have the last phase to compare. So for prime and store, in the probe phase, we use a NAND gate. What it means is that, so when we probe all the cache set, and only if everything, well, if everything are cache, but it is true if some of them are not cache. So this is like the setup. So we probe all the cache set, and then we store the result. So we do multiple probe of the same cache set, and then we store the result. So that's why we call it prime and store. So we store the result. And why are we doing that? We store the result because we want to decouple probe from timing measurement. So the problem with prime and probe, the original attack, was that when you probe, you need to do the timing measurement at that moment. But what changes here is that we probe and then we store the result. We haven't done any timing measurement. We just store the result, and later on, we will do the timing measurement. So here, when we probe, we use NAND gate to probe, and then we store at some location. And later on, when we want to measure the time, we amplify the signal. We use that NOT gate, like a layering of NOT gate, to amplify the signal. Like that. And so we can decouple probe, step, and timing measurement. And with that, we try with attacking egomol encryption. So with slow clock, meaning that low resolution clock, like reducing the timer resolution. And by this, we show that the countermeasure of reducing timing resolution doesn't work for cache attack anymore. So it's so powerful that it's not just bypassing one particular attack, but bypassing the countermeasure itself. So basically, it doesn't work anymore. So that's the first part of my presentation. Are there questions on this one? Yes.
You are kind of assuming that the adversary controls one of the processors.
Yeah, so there's some setup that, so for this particular one, we need to have share cache, not share in the sense that we have different processes, but we use the same, like different calls, but we use the same cache.
We are able, the adversary is able to run a particular program.
Exactly. Yeah, exactly. So we have like two calls, like victim call and spy or an attacker, even, and then we have share caches so that we can intervene with that part of the cache. Well, I shouldn't use the word share caches because that could be confusing with multiple processor. But I mean, this one, the same processor with like different cores on the same processor. But I mean, you can use different similar ideas on a different shared resources. Any other questions for this one? So I guess I will not have much time for the second part, but hopefully just to give a rough idea for the second part on evict spec time attack. So what I shown previously was that cache hit is fast because you access cache and serve from the cache. And cache miss is slow because you need to access the main memory. So this is really the fundamental concept for cache timing attacks. So all the attacks in the past is just like that. But the question is, with all new optimizations, is cache miss really slower than cache hit? We did some experiment, and this is what we would expect. So on x-axis is the execution time, like fast, slow, and on y-axis is the density. So we run a lot and we see like how many, like you can think of probability or something like that. So you would have thought that with cache hit and miss, the timing should be different. So miss should take longer than hit. This is fundamental concept. But then we also got this. Hit and miss are nearly the same, nearly indistinguishable. So what's wrong? Are we saying that all the past research is wrong or what? So what we did with this experiment is this one, 2 lines of code. So the first one is linked list, so access, like linked list. And the second one is just access location. So for the picture on the left hand side is where linked list is cached. And then cache hit and miss is for the second line for accessing PTR. So what happens is that, so if linked list is in the cache, then there's timing overlap in the sense that the first line and second line is quite small because the first line you can do it immediately, but second line you need to wait to get the data from the memory. So there's not much of overlapping. So we can really see that, okay, first line is already finished. We cannot execute the second line because we are waiting for the data. So that's why it takes quite a long time. But on the right-hand side, what happens here is that if we say the first line, if linked list is not in the cache, meaning that to do the first line, it will also take time as well because it's not in the cache. The second line will also, so what I try to do is that it try to optimize. So there's a lot of overlapping between the execution of the first one and the second one. So when it tries to do the second one, so it cannot because it's already, it's like kind of like getting data for the first one. And so it is kind of like slow, but then it's already getting the data for the second one as well. So it's a lot of overlapping. So we see that the hit and miss is the same. So it's kind of like contradicting the previous research that hit and miss are not the same. There could be cases that they are the same. And then what does it mean? So to kind of summarize the observation, so with the out of order execution, so with the technique of optimizing, we try to execute something ahead of time, not following the order of the original program. But then it can do this up to the limit of available resources. And the reason that miss is not always slower, so we need some condition for this, that if there are enough instruction ahead that we could bring, then it will try to execute those instructions. And the latency, like how long for those instructions. So if it's like so long as cache miss, then it's kind of like overlapping or hiding, or you can imagine they try to execute things somewhat in parallel. They try to go ahead and try to do that. So that's why we can see the effect of hiding the latency of the cache miss. And we also found to observe, not in the graph that showed previously, but the latency of the cache miss itself is not constant. It's not like if hit is 1 cycle, miss is 100 cycles. It could be that miss could be 100 cycles or 70 cycles or 25 cycles. It depends. And with this observation, we see that if we can somehow control or manage how much overlapping, how much we can hide the latency of the cache miss, because it's not constant. So if we can hide, we can selectively hide, then we can somehow identify when the miss occur. And if you know previous research on evict time, there was a previous attack called evict time that they know whether cache miss or hit occurs. But with evict spec time, with speculative execution, we know not only whether hit or miss occur, but also when, like when in the execution, when exactly that miss or hit occurs. So like in the first observation, you might think, well, we cannot distinguish, so does it mean that we cannot do cache attacks anymore? But we turn this into an advantage, that we can have a more like fine grain to identify where it occurs. So I don't know how much time I have. Yeah, I still have a bit of time. So overall, like a concept of evict spec time. So we have evict step. So this one, we want to kind of like imagine like the setup phase to know what's going on. And then we evict part of, so at the beginning, we don't know like what's going on in the cache, and then we want to set up. So we evict part of the victim memories in the cache. So we know that it's already not in the cache because we evict. And then we let the exim execute, and then we measure the time. And then if it is slow, then there's miss. But if it is fast, previously we say that it is a hit. But now, if it is fast, it could be either no cache miss, or the miss could be early on in the stage. So because it's so early, so it tries to execute instructions after that. So it's kind of like hide the latency of the miss. So, yep. And just to quickly show an attack, we show an attack, questions? We show an attack on this AST table. I'm not sure how much you know about this AES implementation, but just quickly recap, because we attack decryption part. So we start with cipher and down to get plain text. So there are many steps in AES encryption or decryption, like add round key, do inverse shift row, inverse subbyte, inverse mixed column, another add round keys, and then there's some iterations, like overall 10, but we loop 9, and then there's a final steps that's not in the loop. So this is like general steps of AES decryption. And we're interested in where, well, of course, where the key is and where there's a table access, because with table access, that's where we access the memory. And then if the index is related to the key, then if we know the index, we know the set, cache set, then we can derive the key. That's where we're interested in this part. And just a setup, if you're not familiar with this, the kind of cache attack, so we say that cache has 64 sets, and with the table, like T table, each has 256 entries, and each of them is 4 bytes, so meaning that it occupies this many cache lines, or 16 cache lines. So steps in evict spec time, we do evict, we let the AES execute, and then we do spec time to measure what's going on due to AES. And we can detect access, so we have the cache set that we monitor, and then we detect whether access or not access. So as a brief comparison to get the sense of how good it is in terms of like comparing to previous work with only evict time, not considering speculative execution. To determine the access, so with evict spec time, we detect access in any round, because this is not that fine grained. But for us, we can target particular round. So for example, we can target only the first round to know whether something is happening in the first round only. But for the general one, they cannot really focus on particular part or particular round. So we can be more specific. So I said first round, but in general, well, depends on setup of the machine. It could be that you can detect different rounds as well, but first round is more interesting because that's where you can get the key. There's no point to attack second round if you get the key in the first round. And in terms of access or not access probability, for evict time or previous work, the percentage is roughly 8%. But for us, because we can be more specific, we have higher percentage, and that's help with improving the attack, which I will mention next. So in general, when we attack, we need to use many samples, and we do the average, and we try to figure out what the secret is. So in terms of the number of samples that we need for evict time, we need roughly 2,500. But for evict spec time, by exploiting speculative execution, we reduce down to only 250. But how can we do that? Because it shouldn't be a surprise, because we have higher probability. So we can detect probability much like a higher. We know whether it happens or not happen. Then the probability is increased roughly by 10%, then the number of samples is decreased roughly by 10%. So yeah, that's the, I don't think I will have time for the second part. It's just attacking an AES, but different kind of implementation. Just general idea is that, so it divides into, for S-box, it used quite larger piece of memory. So we split it into 2 steps to recover 2 more significant bits using indexing, and the last one just recover the remaining. And just the concept. So we have this piece of code, and we try to manipulate how much instruction can fit into the cache and how much it can execute ahead. And with this one, we just play around. So the last line is AES decryption, so the ones that we want to attack. And we just play around by having access to memory, and then to memory locations, and whether it is in the cache or not in the cache. And then we play with how much ahead we can let instruction inside, or like the pipeline of execution, by having knobs here and there, and we can adjust and play with it. And with that, we can control how many instructions can fit into the pipeline. And we can detect like when, instead of whether this cache hits or miss, when exactly, by adjusting adjusting the number of instructions that we fit into execution pipeline. And yeah, that's quite brief for the second one. But just to wrap up, like from the first part with logical state, we say that cache attacks are Turing complete because we can build NOT gate, NAND gate, NOR gate, or whatever gate for that. And we have amplification techniques with those gates that we can able to detect with slow clock because we do the amplification. And with prime and probe, we decouple the probe step from timing measurement. So that's how we can use the amplification. And for the second part, we see that hit and miss, they might not have the same latency. And even with that, miss latency is not constant. And with this new attack that we exploit, speculative execution, we have another dimension, not whether it's access or not access, but also when exactly. And if you are interested, so the first part is from Usenik's paper last year, and for the second part, it will be presented next month at CHES. And if you have questions, feel free to ask me.
Any more questions from our attendees?
Yeah, sorry, I'm late. Just to catch the end. I don't know whether you talk about the attack on SGX. Yeah, I wonder how it affected SGX.
So for this one, we did not try SGX. We just do like a normal attack. We didn't try with SGX. Yeah.
Thank you. Yeah.
Thank you, Chitchanok, for the presentation. This might be kind of like a naive question, but I'm wondering if you are using kind of like a cloud provider, technically multiple users are using the same physical devices, or although they might be somewhere else in another part of the world.
So sorry, can you repeat?
So if I'm a cloud user, and let's suppose I'm the adversary, and you are also using the same cloud server, and let's suppose that we end up using the same physical machines, could I try to do something like this, or I just don't have enough control and information to exploit these cache attacks?
So I have to say it depends on which cache attacks, because different attacks, they require different privilege. But in general, if you are like share resources and somehow you can intervene, then the attack is possible.
So do you think the attacker might have that much control, or for like in the cloud setting, or
So I mean, so I don't know like what cloud providers protect, prevent, or have. So it could be that cloud providers, they like one of countermeasures is to have isolation. Like you cannot really like mess with other cloud users. So that would be something obvious. But even for that, I mean, it depends on the attack, on how much. So I mean, if that works, so probably fine. Otherwise, if they could have some channel to intervene, so that's different story. But if that doesn't happen, like two users can use the same physical machine, then it's again how much like power privilege that an attacker needs to have. Like for this one, it's what I presented here is that as long as you like share, like have cache and you can evict cache and you can detect, so that is kind of assumption that you can do, and somehow you can measure the time as well. So then you can do this kind of attacks. But there are some other attacks, like for example with the evict time like attack. So there are other attacks that they require more control, like a OS control, to be able to play or detect something. But in our case, we didn't require that much of power. So I mean, it depends on what kind of attacks.
Okay. Yep.
So, sorry, I have another question. So I wonder, so how the existing countermeasures can prevent the new cache attack. So yeah, for cache attack, we have hardware or software countermeasures like cache partition?
Yeah, so I mean, again, so with isolation is really an ideal case. If you can isolate the thing, then, well, one of the things that make cache attacks possible is share resources. So once you share resources, then you can intervene one another, and there's also some branch, well, some people classify it as contention-based attack. So when you share resources, you can try to make like a jam resources or make resources unavailable, and that's how you can detect what's going on. So if you can prevent those from happening, so that would be ideal cases. And like one of the previous countermeasure that they try to reduce time resolution of timer, but I mean with this new technique we show that it doesn't help anymore. Then we need to use like some kind of other techniques. Like for example, if we cannot measure the time at all, so for example there's no way to get the timer, it will make the attack more difficult. But the question is whether we can find another channel to get the time, like maybe not the real time, like the number of time, but like just to have the sense of how fast, how slow. So I mean, I said I cannot say like the exact countermeasures because it's kind of like the game of attackers and defender. So yeah, so we can try to have something to prevent certain type of channels, but there might be multiple channels for attacks to happen.
Thank you.
No, I think I'd like to thank our speaker. Thank you very much.